Uh, my name is Balkrishna, Associate Professor, Department of Engineering Design, IIT Madras, and I am here on ICCR Visiting Chair Professor, awarded by the Ministry of External Affairs. And today I am going to talk about the factor of frugality. This is more from an engineering point of view, how to build these things from scratch with the potential that they have shown over the years, especially when you consider climate change and a sustainable response to that. And I think first have some, people to thank, institutions to thank. So just repeat this from yesterday. So just kindly bear with me. First, thankful to Ministry of External Affairs, Government of India, who made this position possible through their arm called ICCR, the Indian Council for Cultural Relations. So this was awarded by Ministry of External Affairs through ICCR. And very thankful to IIT Madras. And this research has been possible mainly on IIT Madras campus. Since I finished my PhD and joined that place, we have been consistently ranked number 1 in India for a long time. Very close tie-ups with industry. We are one of the first ones in India to have a nice research park. A lot of industries collaborate with us, and a lot of exciting things happening on IIT Madras campus. And very nice world-class infrastructure, very talented faculty, very nice students to work with. And over the years, all this has helped to take this research forward. So once again, very thankful and grateful to IIT Madras. The other institute I'd like to thank is Leibniz University, Hannover. Very grateful to Leibniz University to make this position possible. Thankful to Professor Ingo Liefner, my kind host and also collaborator on some of these projects in frugal engineering, who made this position possible with the ICCR position. The other person is Dr. Bala Ramani. He's not here today with us. He worked with Professor Ingo Liefner and made this position possible. So there was a lot of behind the scenes work that he did. Worked a lot, I'm told, and very thankful to him for doing that. So without much further ado, I'll start today's talk. So I can safely say that until now, the engineering that we have been practicing is pretty conservative. Engineering principles are pretty conservative. What I mean by that is, typically, in many cases, we end up using more materials, more resources than what is maybe necessary. And this leads many times to more greenhouse gas emissions, okay? You can generally correlate the two. Also higher cost, and there is also excess material resources. Okay, so, and what we are seeing in the last, I think since the Industrial Revolution, with the start of this technology and engineering playing a big role in our affairs, it has also led, in a large way to this problem of climate change and other planetary crises that we are currently facing. So things have to be done differently from here onwards. There is only a single Earth, the resources are finite, and I think we have to manage this very well. There is also a population that is growing, and a lot of people are now coming to the levels where they want to enjoy many of the goodies that we take for granted. So, and I think engineering can respond to this in a very nice way, in a very sustainable way, and it has all the technology and everything possible now to make this happen. And what we are suggesting from this point of view is frugal engineering. The entire frugal movement started, I think, a little more than a decade ago, to my knowledge. It had very humble beginnings, very simple products called frugal innovations. And this was basically helping an ecosystem or people who had natural scarcity in resources. So very clever inventions were built at that time, and this helped to kind of get over many of the problems, and the functionality was also not bad, quite decent. And slowly this started developing, and over the years, a lot of companies and many research efforts have been directed towards it, where formal engineering, science, or any other knowledge area has been brought to bear on it to use these principles to make something better, in the sense affordable or low cost, lesser resources, and good functionality, very good functionality in many cases. And so the frugal innovation concept has also grown or evolved from what were known as frugal innovations to something called advanced frugal products. So they use the same principles as, they're based on the frugal innovation concept, low cost, lesser resources, good functionality, but now we are bringing formal engineering principles to bear on them. And the beauty here is, other than traditional engineering principles, many of these products need cutting edge research to work on them. It's interdisciplinary, okay? It's not, kind of limited to any one discipline. You need everybody to work together, different departments, and many times it's a cutting edge research. And just to tell you, you take any product and make a frugal version, there is a high chance that this might be something totally new that you're giving to the world, okay? It might not be the same as what came in that family. So that's the beauty of, this frugal engineering principles. And sustainability is in a way built into it because it takes lesser resources, typically lesser emissions, and also trying to make it affordable so you can improve the living standards by, making such products. And I'm sure there are ways to involve sustainable development goals, the other goals of that, into these products, okay? And engineering can make that happen. You can tweak many of the principles. So, frugal engineering is to streamline products, consuming minimal material resources, robust functionality, very good functionality, or I'll say excellent functionality, low cost or affordable. And in this regard, there are engineering itself, right, and its constituents will have to change. Engineering is composed of numerous constituents, right? You have design, materials, manufacturing, quality control. This is just a crude decomposition of the main engineering. But any activity that leads to any engineering can be frugalized. And I'm going to talk about some of these today to you. And so this is, I think now the entire frugal innovation movement, I can say that has matured into something called a frugal engineering. And there are many companies and other entities that are doing this without knowing about it. And at least I've come across, many researchers, many companies, showing products which are very good in their functionality, and they've consumed, little resources, and they're affordable. It's just amazing to see that. And what this new discipline tries to do is to systematize engineering to make these things possible from scratch. So that under one umbrella, we can collect, all kinds of techniques, all kinds of methodologies which can make this possible. Some of these are already available. We just have to use them in a different way. And for others, we'll have to look for newer methods to do this. So under all of this, there is one way of attacking this is through what is called the factor of safety. And I think my engineers here will agree with me. We always use a factor of safety for designing any product. Okay, mechanical, civil, you take any product, it has a factor of safety into it. Classical design, is based around a reliability approach or the factor of safety approach. And the factor of safety, as the name suggests, was started so that to give a feeling of safety for your product. So nuclear industry might have a factor of safety of 5. And an aerospace industry typically works with around 1.3 to 1.5. And the lower the factor of safety, unity is of value 1, basically means that you're operating at a failure load. Okay, so higher factor of safety, you're operating well below the failure load, the maximum failure load possible. You don't want to go beyond that. So typically, higher factors of safety are recommended so that you can be more certain about your design and what you're creating. But this also results in using more materials, and it doesn't make the product frugal. So the first thing is to kind of go for a lower factor of safety. Okay, typically 1.3 to 1.5 maybe, but again, this will depend on the product and the sector concerned. Okay, a factor of safety which is good for one area might not be good for the other. Like for the nuclear industry, I told you, you have something like 5. So, 1.5 is kind of very risky for the nuclear industry. So you'll have to think for an appropriate value there. But when you have a lower factor of safety, you're using lesser materials. So your design has to be very rigorous now. Okay, there is no room for any failure in your design. So your models, your material data that is available, everything that goes into your design has to be very accurate and very rigorous. And this is also possible now because a lot of these things are available and also affordable. And so that you make your design rigorous and you consider all the loading scenarios that this product will be exposed to. And this is also now accompanied by what is called material saved. So the factor of this new thing, right, is called a factor of frugality. So it is based on the factor of safety, wherein it takes a lower value to start with, rigorous design. And then the MS, or the material saved, it follows every stage of product development. You start with design, then you go into manufacturing, then you go into maybe quality control and all of the other things until the product is out there. But at every stage of your product development, you can keep saving or more and more material. That's how this thing works. So when you start with a low factor of safety, you are going for lesser material. Okay, it's just built into it. Then the next stage is manufacturing. I'll show you this with an example. The next stage is manufacturing, where there is more room to save material. So it gives you a lot of these options in different stages, and all this is nicely quantified in the factor of frugality. A symbolic representation is f raised to s. So f is a factor of frugality, and s is a traditional safety factor. So it is subsumed. It is taken inside your factor of frugality. The example I will use is a shaft, mechanical shaft. This is like a workhorse of engineering. You use it in so many places, either to transmit power or to convert, rotary motion to linear. It has like many applications, but also very easy to understand how this, how design works and how the factor of frugality approach works. Engineers will know this, that for a given factor of safety, a hollow shaft that you see here, right? It is hollow, has better structural integrity, okay, compared to a kind of a solid shaft. So for the same factor of safety of say 1.5, I have these two designs, but this also saves more material and it is better structurally. So the way I do this for a shaft is, I start with a very low safety factor, as you can see here, 1.5. My baseline design is a solid shaft, okay? The next stage is to, in design, within the 1.5 family, what other design do I have which will save yet more material for that design? So here I select a hollow shaft. So for 1.5 safety factor, I go for a hollow shaft, which other than saving materials coming from a low safety factor, saves yet more material from the hollow feature. Once you fix this part, you go to manufacturing. Now manufacturing, either I can take a very solid bar stock and bore it, machine it to make it hollow, in which case you are wasting material now, or I can do something called extrusion. Okay, the nearest thing that comes to extrusion is your toothpaste in the morning, right? When you squeeze it, that's the process of extrusion. So you can actually extrude metals. But the beauty here is you're not wasting material. I can use the right volume of material to extrude and get a hollow shaft without wasting any material. And I'll get a required finish and all the other properties that I want. So by doing that, I've actually saved more material here by not going for machining. And finally, what if I go to the junkyard? I'm crudely putting this as junkyard. Junkyard is now a big business, disassembly, right? So there's a lot of engineering that goes into it. All your sustainable products have to be disassembly friendly. Like they easily disassemble, or a lot of other features are built into it, so you can reuse them, okay? Either directly or maybe melt them and then use it in a different form. So this is like a big industry itself. So what if I'm able to find a shaft which is hollow and extruded that I wanted here as an end-of-life system. Somebody has just left it, I can just use that right away. So again, you're using more material here. So this is cumulative. It keeps on adding, and finally it gives you a composite score. So we start with a factor of frugality of 1.5, which is just your initial safety factor, but I end up with 4. And the way this has to be interpreted is, for a given safety factor, a low safety factor, my factor of frugality has to be as high as possible. I can make this artificially high by taking a higher safety factor, but remember that is not our goal. We want to save material to make this frugal and better. So you go for a lower safety factor. So for a given low safety factor, the higher my factor of frugality, or F, it is better. So this is a thank you, Julian.
Let's try if it's not working. Okay.
Yeah, it works. So the same thing here, again shown in the table form, and like I told you, we start with the baseline design, and you just equate your factor of frugality to the baseline factor of safety. And then one by one you start adding, the alternative design, the hollow feature, then the alternative design and manufacturing, finally alternative design, manufacturing, salvaging, together with a low safety factor gives you a cumulative F value of 4, which is supposed to be very frugal. Now, the factor of frugality accounts for all kinds of techniques, models, and materials that are available to any engineer from any sector. So materials are very important, because you can affect a design with the right choice of the right material. This can affect your factor of safety, the strength, the properties, in fact the functionality. So you can actually pick maybe, ceramics, metals, polymers, depends on your application, composites, and even within a material, right, you have different crystal structures which are, lend themselves to shaping them, and also from a functionality perspective. All this is accounted for by the factor of frugality. So anything happening in traditional engineering, you can use it in this approach. In fact, material properties are very important from a frugal engineering perspective. By having the right material properties, I can actually influence how much material I'm consuming. I can impact the frugal characteristics of a product. I can make it very robust in functionality, better in functionality, lesser materials, lower the cost. So this is kind of the secret behind all of this. And for a given material, your phase diagrams, what kind of material do you want, heat treatments, post treatments, anything that you're doing with your material and processing can be used in the factor of frugality. So in short, any of the traditional engineering principles can be used here. One nice thing is, materials like wood, and this group from Purdue recently has shown forming and forming capabilities with wood. And this was based, I think, with a group in India, wherein they are taking the areca sheet, and you can make plates and all kinds of these nice articles out of it, and using forming principles from metal cutting. That is the beauty of it. Okay, you might think wood is very kind of brittle, and it might not lend itself to it, but wood has good. It can be shaped nicely if used properly, and you also need to kind of hydrate it, mix it with water or other solvents to get good, how do I put this, malleability or formability for wood. Wood has been used for making bites, bamboo bites, because bamboo can be heat treated to give good manufacturability and also good properties. And in fact, if you see here, this is very interesting from a sustainability perspective. The traditional plastic cups and probably also paper cups and all those things we take for granted, they have a higher embodied energy compared to palm. And this is completely degradable. You make something out of palm, right? You can form it into all these utensils and whatnot for this application. I can actually degrade it, use it again. The embodied energy is quite less. Very sustainable, very sustainable. And engineering actually makes these things possible. I think many of you might know this. This entire building is made of wood. I think this is now turning out to be a very good trend. Wood has really good, properties as a construction material. Yes, you need to treat this properly before using it, but it's doable. It's a very sustainable solution, okay, and also traps the carbon. Very nice to know about that. And you might think that it's inflammable, but those things are taken care of when these things are constructed. This was, I think, a picture taken in Canada, okay, a wooden house. This is something we did in our group. My master's student has used the factor of frugality approach to design a part of a rock crusher, and we're trying to patent this, and he's also trying to commercialize this product. Now, one thing with the products that are designed frugally, through frugal engineering or factor of frugality, they're designed from loading that you see nominally in a given environment, right? But typically you can't predict that. You might always have room for some overloading. What if there is a perturbation? The load, increases suddenly. So how do you account for that? So one way of doing that is by using something called complex systems, right? I think yesterday I briefly touched upon that, and I told you that complex systems are systems in which they include multitudes or many agents who have very simple interaction rules, but when they interact at such a very large scale, there is emergent behavior coming out of it, okay? Behavior which you cannot predict. So if you take a large number of ants, right, and just leave them out there, they can do many things, either build an anthill, or they can maybe forage, or carry some food from here to that. That cannot be predicted, but you can make them do all these chores. But you can engineer these systems to kind of get very close to what you want to do them for you. So one example here is an electric vehicle, right, which is very popular and also being touted nowadays as a sustainable solution to what we are doing. Definitely an electric vehicle with a utility or a grid which is also green is the best combination to have. One way to kind of make this frugalized is to design every component with a factor of frugality approach. You make a frugal design for every component. But now, like I told you, these are designed for nominal loading. So to make them resistant to cases of overloading, right, which might arise during day-to-day service, you make these products adaptable. You give them the feature to adapt, maybe morphing, some suitable technology where they can change in shape. Okay, this can make a big difference. So, and when you put all these vehicles in a big network, and when they are talking to each other, and there are many of these simple interaction, so you can engineer some kind of a complex network with them. And so this will lead to what is called a frugal griddable electric vehicle. So you have an electric vehicle which is designed from the frugal principles, and now it is connected in a big network, hopefully engineered for complexity, so that what this does to you is it tells the vehicle or any given vehicle in the network of an impending failure, and it can take an action, either shut itself out completely or maybe morph or take some action to safeguard itself. So that way you are enhancing the longevity of your electric vehicle, and it also helps in mobility, transfer of power. You can manage all those things very better. So there's one approach of doing that, having sorry, this is kind of stuck, Julian. Sorry, I think this one is stuck. This is stuck.
This is, oh.
Sorry about that. The board is not completely smart.
It's not frugal.
Not frugal. No.
Over complex.
Or maybe it's frugal in a bad sense.
I would rather
Rejection of the wrong functionalities.
but I would rather think that it's hyper complex, and then
Oh, yeah.
when something goes wrong, then it's not resilient enough.
My experience is it looks complex, but it is not that complex.
You're rebooting it?
Huh?
Rebooting it now?
Yeah.
It's usually what we all do. I think that there was a joke in the US. When I went to the US, they used to talk about computer-aided design, CAD. But everybody was a CAD expert because they used to do control, alternate, delete to reboot, right? So anything happens, you do CAD. So the joke was, yeah, we are all CAD experts. You don't need to know that. It's taking time, right?
Yeah.
I have a question.
Yeah.
Already.
Yeah,
So the material safe factor, right?
right.
How is it measured in terms of like what does the value of one mean?
What is the value of 1 mean? Okay, I don't have a blackboard here. You remember that chart I showed you? So if you take any metal, I take a metal as an example, and you load them. We have something called a very simple tension test. Okay, it's a very simple test to characterize material properties in the laboratory. Okay, and which can also be used in handbooks, and this is used in all real life applications. So you pull this material apart, right? You keep pulling it, and you keep recording the load versus elongation, how much it extends. When you plot that, that will tell you that there is something called an elastic regime for a workpiece, or any metal or any material, and there's also something called the plastic regime. Elastic is simply, you put a load and you release it, it goes back to the original shape, like a rubber band. Okay, that's what is elastic. So most of your structures here are loaded for elastic loading. You go into plastic, that is kind of failure. So factor of safety, typically, most of the applications, it puts you in that elastic regime. Okay, so it's a linear, and then you have a curve there. So where you are on that linear part. So a safety factor of 1 will be very close to that transition point between elastic and the plastic region. And if you take a very high safety factor, it puts you down there. So there is no danger of getting into the plasticity zone.
Okay. But that's factor of safety, right?
Right.
And like the other component, like the material safe factor?
The material saved is, it just quantifies the material saved, like say the weight of material that is saved. For manufacturing, how much are you wasting, right?
Okay.
And for a design, I can weigh the two designs and then crudely measure how much material has gone into each and what the saving is.
So, like,
So it's a number that is added to that.
so maybe like the factor of 1 would be no material saved, and the factor of 2?
That depends on which, for salvaging, like end of life, 1 means the whole product is salvaged, right? Completely changed. So that is good. So for manufacturing, you go sometimes maximum to about 50% savings in how much you are saving on waste.
Was this the right side?
Yeah. Thank you. Thanks, Julian. So here's a snapshot, just a very quick snapshot of how, a complex network, not a real one, but a schematic. And you have all these griddable frugal electric vehicles, the dots here, right? And along with the grid, smart grid utility. So such a complex system can be engineered, maybe even for other products to give them more resistance from the resilience of a complex network. And such an approach can also be used for other products. Okay? And from this perspective, a frugal product will be a local complex network, and you're putting all of them in a big complex network wherein it networks all these products together. The other stage is manufacturing, right? Manufacturing offers you like so many processes: casting, cutting, extrusion, like we talked about. Non-traditional, wherein we use material like water to cut materials. You won't believe this, but water under very high pressures and speeds can actually cut a block of granite. Okay, so, and these are the applications where you need that, where you cannot use conventional tools available to cut or manufacture materials. Powder metallurgy, I can take powders, consolidate them, and make them into parts. And additive manufacturing, right? The recent buzzword that you see around. So many choices to make, and how do you go about that? And this is where we come to the topic of frugal manufacturing. Again, from a factor of safety perspective, what we are trying to do here is save more on waste. So I need to get minimal waste or maybe zero waste, but I also want to make a product which is the best in its properties, like surface finish, integrity, like residual stresses, all of that. You get very good properties, but with lesser wastage, and also low cost manufacturing processes. Okay, so you're going for minimal number of low cost manufacturing processes to give minimal waste, okay, with the best quality for your product. So ideally, I want one process, low cost, giving zero waste, and giving me what I want, like, all the features and all the characteristics, tolerances, surface quality that I want in my workpiece. Now, there are some case studies here. One is superplastic forming, and this is many times used to make a lot of your components, critical components for the aerospace industry. And here you see, like part here, something like titanium, and you have a high pressurized gas that forms it, okay, and it gives it the shape. This is heated to a certain temperature, so it becomes manufacturable, and then the gas actually shapes this against the die that is shown in yellow, okay. And typically this is followed by heat treatment to give the right, what we engineers call the microstructure, right, or to give the right properties into the workpiece. Now, this is not frugal now because you have an extra process here. So one way of making this frugal, right, is to combine the heating or retrofit your main, right, forming die, superplastic forming die, with heating, so that you can do both in one and save costs in the process. This is one way of doing it. I'm not saying it's the only way, but this is how you can shape, many things in manufacturing to make it low cost and give you and serve needs of frugal engineering. The other example is from metal cutting. Typically, when we have to shape something, like we want a flat feature here for this workpiece, you typically take a couple of rough passes, remove a lot of material, and then you take the finishing pass to get what you want. And then we do something called shot peening, which is you just aim a lot of these high projectile steel ball, indenters at the part to give something called residual stresses in the subsurface region. Residual stresses are very important, by the way. Okay, so all products have this. What you see for a product is only the finish, but all manufacturing operations leave a residual stress in the component, and this affects the functionality in a big way. Many times you can improve the longevity of a product by just giving it the right residual stresses. Now, the one way to make this frugal, avoiding these two rough passes and short peening, is to do what is called high-speed machining. So I can machine at very high speeds, okay, in a single pass. I'm removing very less material here by doing that. But speeds are typically like, they vary for different materials. And for aluminum, many times it can be like about kilometers per minute. Okay, these are very high speeds, but it gives you a very good finish and the right residual stresses. And for such a case, you can see that you're saving about 90% of material wastage, just opting for high-speed machining. And this is doable. Most of the machine tools you see now have this feature of high-speed machining. Different materials have different high-speed machining regimes, but you can program your machine tool for that. The last example I'm giving is from additive manufacturing, and this is a component made from titanium, Ti-64. Ti is titanium, 6% by weight aluminum, 4% by weight vanadium. It's a very popular aerospace marine bio alloy. In fact, I'm having a Ti-64 drill bit in my tooth right now, okay? So my doctor accidentally left that while doing a root canal, and I think I'm a living example that it works well, and it's perfectly compatible with the body. But manufacturing Ti-64 is a nightmare. Okay, so many times the materials that are very good in terms of their properties are also very difficult to manufacture. So from a 3D printing point of view, you put a powder, right, of Ti-64, and then you have a laser beam that is moved in, scanned in different layers, and in the process, it sinters portions of it. Sintering is like bonding the particles together to make a part out of them. But if you use it the way it is, it gives you a microstructure which is columnar. Okay, you can see the stripes here. We call that a columnar microstructure. A columnar microstructure is not good. It gives, in engineering parlance, what is called anisotropy. Your properties vary with direction. You don't want that. So first of all, you have a columnar structure. And secondly, the composition here is something called alpha prime plus beta. You want alpha and beta phases, but you get alpha prime, which is acicular, and you don't want that here. So by using the way it is, I'm getting a columnar grain structure, and I'm getting a wrong alloy to start with. Later, I might have to heat treat this to get the right grain structure. Meaning, I want to avoid the columnar structure and make it something called equiaxed. So I get isotropic properties. Okay. Sorry for my engineering jargon, but I think that is a bit important for this presentation. And later, you might have to do finish machining to, get the right finish, and also maybe residual stresses. One way to frugalize this is to use a heated substrate. You mix your powder with an inoculant, and this inoculant with the preheated substrate makes this equiaxed, okay, which gives you isotropic properties. It also gives you the right alloy, and you might at the most need a finishing cut to make this better. And I'm sure that with time, I think we are now getting into models of hybrid machining, where hybrid manufacturing, wherein the same machine will 3D print and also machine to get what you want. So there is yet more scope to reduce waste and make this more frugal. So I'm going from all these processes to just one extra, but getting the right alloy with the right structure. That's more important here. And so this can be used to design the new generation of frugal machine tool systems. This is very important now, okay? We want machine tool systems which are intelligent to take decisions, right? When they are wasting more material, and also what kind of properties they are imparting to the workpiece. And this is doable now with artificial intelligence, big data, along with machine tool technology. You can combine these things, and you can design the different structures of a machine tool with factor of frugality, and you can use all these tools in Industry 4.0 to make this possible. This is a frugal machining cutter that has been designed by my student. And she's doing PhD with me currently, and we have used frugal machining principles to make a cutter which is, I would say, kind of smart. So it avoids something called chatter. Chatter is a self-excited vibration. It's a very bad vibration phenomenon to have in manufacturing. It affects the property, it damages the machine tool, and also there are, might damage the operator too. So very problematic to have it, and you have to avoid it. So we have tried to build in features in the cutter to avoid that. So that also saves on the waste, reduces the cost, helps in getting the right properties. And by avoiding chatter, I can also avoid a lot of other parasitic mechanisms that are inherent to machining. She's currently on a scholarship with Purdue. She is finishing up this work at Purdue University. She'll be joining, I think, soon in mid next year, hoping to, she'll be graduating out soon. So this is a longitudinal, turning cutter that we are planning to, we have patented the idea, and hopefully also looking forward to industry and other collaborations to take this to the next level. And I think, lastly, the beauty of the factor of frugality, it's a single number, okay? It's a single number that you get, but you can nicely control it with the different features that it offers to get what you want, as opposed to a reliability-based approach to design, which is stochastic, right? It depends on numbers. You want more data, it also tends to be more expensive. There are advantages to it. I'm not saying, it's totally bad, and I'm sure FS also has its own disadvantages, but this can be tweaked to work better and better with time. And this will help you to build in sustainability. That's the beauty of it. You can engineer that. I can actually, impact like how much material I'm consuming, the cost, the functionality that I want. So a lot of these things can be done with frugal engineering. And a factor like the factor of frugality will also help you to compare products. So within a family of products, I can just compare the F value and figure out how sustainable they are. Okay, and it also tells you it's affordable, it's also frugal and good to the world. And caveats for the factor of frugality, like I told you, it varies with the sector. So there is no one number or one safety factor that works for all. So we have to make the decision in the area where we are working, and accordingly tune the factor of frugality to your sector or your application. Constraint on resources. the advanced frugal products. This whole thing is based on the advanced frugal products, like frugal products for that are seen in more engineering applications. We build them with an artificial constraint on resources. That's the definition of an advanced frugal product. You build it with an artificial constraint on resources, and you use science, engineering, or any knowledge area relevant to design it systematically from scratch. So by doing that, right, you're actually, again, like I told you, building in sustainability issues, sustainability credentials into it. Okay, that's one nice thing about it. Rigor is very important here. Okay, like I told you, because lesser materials, so our models, our designing has to be very rigorous. There is no room for errors. And the human factor, of course. So applications where the human life is at stake, nuclear or maybe healthcare, one has to use these things with a certain amount of research and also due diligence. It's doable, but you should not hurry through it. Okay, take your time, get a good product out so that this helps in all ways possible. And I think question and answers we can do now, or maybe later after the other talks are over. I leave it to the audience. Thank you for your time.